We were here last time. So let's look at what we are doing at this point. We want to compare two growth functions. When we compare, we calculate the limit of the ratio of these two growth functions when n goes to infinity. And there are four cases. For these four cases, when we do the comparison, we use some concept called the order of growth concept to describe, how fast they grow. Yeah. But here, because at this point, I didn't give you the definition of this order of growth concept. But here I can give you some concrete example. Let you see what we are talking about when we say order of growth. Yeah. Here I want to use example, the power function as the example. When we have a power function, yeah, so the form of power function is n to the d. Okay? Yeah. The variable n is the variable. Exponent number is the d. It is a fixed number. D is a fixed number, fixed constant. Yeah. And for this power function, definitely, this d number should be greater than 0. Okay, positive number, but not necessary integers. D could be, real numbers, not necessary integers. For this power function, then the order of growth. So we can easily get this order of growth. That's the D. Okay? Very simple way we can get this concept, order of growth. Yeah. But there is one special function when we talk about order of growth. It is pretty hard to describe its order of growth. That function is log function. Log function, yeah, very special. Log of n. Yeah. Base a, we assume a greater than 1. Yeah. For this log function, if you talk about order of growth, you will see there is no appropriate number you can use to represent it. Yeah. So at this point, I just raised this question because we haven't learned enough knowledge to understand why we couldn't find appropriate order number for log function. Yeah. Yeah. But after we complete part C, we will get it. Yeah. We need to get some results. We need to derive some results to help us understand this log function. Yeah. So, yeah. Then, the next step, we want to do a little more when we describe the relationship between two growth functions. For case 1, case 1 we know that is the current fact like this. Yeah. But we like to have some compact notation to represent case 1. Yeah. We want to use some special, simple, concise notation to represent case 1. That's the main topic of this Part C, asymptotic notation. Yeah. Here we want to represent in this one. F function belongs to little o of g of n. Little o, yeah, that's the asymptote. Our first asymptotic notation, little o. Okay, very abstract, yeah. Yeah. Very short, very compact notation. Yeah, so very convenient to write. What's the meaning? The meaning is simple. If you see this notation, the meaning is the limit of f function over g function when n goes to infinity equals 0. That's the meaning. Yeah. But we don't want to write a lot of words. We want to use a simple way to represent it. So for that reason, we use our first asymptotic notation. Similarly, for case number 2, this case, we use our second asymptotic notation, big theta. Yeah, big theta, not little theta. Okay, sometimes we use, big notation. Yeah. All right, big theta notation. Yeah, that means these two growth functions have the same order of growth. If we use the limit way, the ratio of these two growth functions when n goes to infinity is a positive constant c. That's the second case. Right. Third case, little omega, our third asymptotic notation. We use little omega to represent f function belongs to little omega of g function. The meaning is the order of growth of f is greater than the order of growth of g, and the limit way, the ratio of the limit of these two functions when n goes to is infinity. Yeah. So we used 3 asymptotic notations for these first 3 cases. But the case number 4, because we don't have the conclusion, right? Yeah, we don't have the comparison result for case 4. So we need to do further study for case 4. All right. Yeah, we know the limit way doesn't work. Yeah. So we have to find a different method to study case 4. So the next question, what is, the method we want to use to study case 4? Case 4, all right, yeah. Using upper bounds and lower bounds. Yeah. This time we need to avoid limits. Yeah. So we use inequalities. Yeah. How to use inequalities? Given a growth function, we want to find its upper bounds and lower bounds to describe a growth function. Using inequalities to replace the limits. That's the idea. Yeah. All right, so let's look at how to use inequalities. Objective, yeah? So here, for this inequality method, no matter this limit exists or not, two possibilities. The limits may exist or may not exist, but we can always use inequalities to study growth functions. All right, yeah. But here, especially for the case, the limit does not exist. Yeah, so then we have to use this inequality way. All right, how to do it? Yeah. All right, because when we use f function over g function, so usually we want to choose the g function as a simple function. Yeah. Yeah. So for example, this power function n squared and another commonly used log function, so n log n, things like that. N log function. Yeah. So power function and the log functions, these functions are commonly used as the g function. Yeah. Simple, but it can tell us information about order of growth. Yeah. All right. Yeah. Yeah. But the f function could be relatively complicated. Yeah. All right. So, but then we need to do some approximation. We want to, simplify f function by approximation. For example, remember we did before, we throw away minor terms. Minor terms. Yeah. So that's the way we simplify it. All right. Now, regarding the upper bounds and the lower bounds. Now we want to find two positive constants, C1 and C2. Yeah. So given function f of n, can we find two positive constants C1, C2 such that this inequality holds? Yeah. That means we use the C2 multiple of g function as the lower bound of f function, and the C1 multiple of g function as the upper bound of f function. Yeah? Yeah. If you can find these two constants, positive constants, then you can make your conclusion. Yeah. All right. You can make your conclusion. And what is the conclusion? Yeah. So we will look at this question next. Yeah. All right. Yeah. And you can see under this situation, yeah, the limit, we can make conclusion even if the limit does not exist. Yeah, because you have the inequality upper bound, lower bound, yeah, but the ratio of these two functions, when you take the limit when n goes to infinity, it may not exist. Right? Remember, I gave you a counter example last class. In that example, you can find upper bound, lower bound. Okay? Yeah. But the limit does not exist. Yeah. 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 So you can see this method solves the problem of case number 4. The limit does not exist. Yeah. All right. Next, we need to look at the definition of asymptotic notations. Yeah. So that part, pretty abstract definition. Yeah. So we will look at the 3 definitions, yeah, but the first one is the most important. Yeah. After the first one, the other 2, similar. Yeah. Similar understanding. Yeah. So let us try to understand the first definition of asymptotic, big O notation. Yeah. Big O notation. Definition here. Yeah. So let's look at the statement of the definition. For a given function g, the notation big O of g, big O, yeah, our fourth asymptotic notation, right? Yeah. So learned 3 before. This is the 4, number 4, fourth one. Represents the set of functions. It's a set. Now, what's the meaning of this notation? A set of functions. First, what set? Yeah. What set? That satisfies the following condition for big O. There exists some positive constant C. Here, we only need to find one constant C. Yeah. Not two, not a C1, C2, only one constant C. And some non-negative integer n0. Some non-negative, yeah. So why this one? Yeah, I will explain that. Yeah. Yeah. So this condition, yeah, very special. Yeah. Yeah. Two constant. Here you can see C constant and some non-negative integer n0 constant. Yeah. Such that inequality. Okay? Upper bound here. The inequality, we want to use the upper bound. Yeah. So we can find the C multiple of G function to be an upper bound of this F function. Yeah. If we can do it, then we have our conclusion. Okay? Yeah. But this inequality holds for all n greater or equal to n naught. Yeah. 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 So here there is this condition we need to include. Yeah. Then conclusion. What's the conclusion? Yeah. The conclusion is f function belongs to this big O of G function. That's the conclusion. Yeah. All right. So this statement actually not easy to understand. So we need to spend some time to understand this statement. Yeah. All right. The first part that's hard to understand is this n naught constant. Yeah. That one. So here we only require, you can see, this inequality holds only after n greater or equal to n0. Now, if n less than n0, we do not need this inequality hold. Yeah? Think about that. All right? Yeah? So that means when n relatively small, this inequality holds or not, it's not important. Okay? It may hold, it may not hold, but it's not important. Yeah? So that's something interesting. Yeah. That's the first thing. The second thing, how do you choose this n naught constant? Yeah? For some non-negative integer n naught, but it looks like not very clear how to choose this non-negative constant n0. How to choose it? Yeah. Yeah. Here, you have freedom to choose. Yeah. You have freedom to choose it. Could be a large number, small number. Yeah. But as soon as you select it, you have to fix it. You have to fix it. Yeah. Yeah. Before you make your decision, yeah, you have freedom, okay? Large, small. But after you make your decision, You cannot. You need to fix it. All right? Yeah. So that's the way to choose this n not constant. Yeah. All right. Yeah. Then, another relatively hard to understand part is this part. I want to explain a little more. Yeah. Why, when n less than n0, not important? Okay. Yeah. For n, yeah. That means the problem size is relatively small. Yeah. So when n less than n0, that is case, yeah, the problem size relatively small. Okay? Yeah. Yeah. In this situation, yeah, the problems are relatively small. We don't worry about the computation because our computers can handle easily. Yeah, problem size is relatively small, right? Yeah. So under that situation, we have confidence. Yeah, our computers can calculate it, yeah, without any problem. Yeah. The part we worry, the part that we really have some concern, that's the problem size, very large. Yeah. Yeah. Remember, so last time I mentioned when we compare polynomial evaluation, for the brute force method, we may need to use 5.8 days, right? 5.8 days. So that means when the problem size is large, to find the result, we may need too much computation time, right? Yeah. So that part, we really worry. Yeah. All right? But not for this part. So that's one way to understand. Yeah. Another way, a little deeper way to understand this part, not important. That is, so think about it. You have good algorithm and let's say two algorithms. One better, one worse. Okay? One better, one worse. Two algorithms. Right? Yeah. When you do comparison for this part, okay? Yeah. Yeah. So we have two algorithms. Yeah. Better one, worse one. They both, we compare them for the relatively small problem sizes. In that situation, the worst one may do faster than the better one. Yeah, that could happen. When the problem size is relatively small, the worst algorithm may perform better than the better algorithms. That could happen. But we do not count. Okay? We do not count. Okay? Yeah? So because the problem size is small. We only count when n is very large. That part we count. Okay? Which one performs better for relatively large problem sizes? That part counts. Yeah? This part doesn't count. All right? So which one faster, which one slower, doesn't matter. So that's another understanding. Okay? Yeah. Why doesn't matter? Yeah. Yeah. So later, sometime I give you, deeper explanation. Sometime later. Yeah. So at this point, I just, give you a first round interpretation. Yeah. All right. Next. Then there is another way people talk about this. Yeah. So if we recall in calculus, so here, if we recall in calculus, people frequently use this sentence when n is sufficiently large to describe this n greater or equal to n0 condition. Yeah, in calculus. Yeah, if you look at, actually, this definition, we used the language from the calculus. Yeah. Then, in calculus, when people write this similar statement, sometimes they want to avoid using n0 explicitly. Okay? Yeah. So there is an n0. Yeah. Sometimes they use it. Sometimes they do not use it. So when they want to skip this n0 notation, they use this sentence. They said, when n is sufficiently large. Okay? Yeah, it's very common in calculus. Yeah. But when you read this sentence, what's the meaning? What do you mean sufficiently large, right? Yeah? Because for different people, the sufficiently large, the meaning is different. Yeah. Yeah. Do you mean when n is greater or equal to 100, it is sufficiently large? Or when n greater or equal to 1 million, sufficiently large? Yeah. You don't know. Yeah. You don't know. Yeah. So the exact meaning of sufficiently large is here. You can find some n0 with respect to this inequality. Yeah. Because when you talk about n sufficiently large, you need to have this inequality first. When n greater or equal to certain integer, positive integer, and 0, this inequality holds. Yeah. Right. Then you say n sufficiently large. Right? Yeah. Otherwise, yeah. If you do not have this inequality, you can never answer the meaning of sufficiently large. Yeah. No base. No base for it. Yeah. All right. So that's another part. Then, if we look at from the graph, we get a visual understanding. Here you can see there is a curve for f function. Okay? A curve for f function. Then g function. Here you can see g function. We use it as the standard. Yeah. So we use g function as the, standard we want to use. Yeah. To get an upper bound of f function, yeah, we can use the multiple of g function. Okay? Yeah, you can use, yeah. If your c value is not big enough, you can raise it, make it larger. But your goal, so you want to make it cover the curve of f function. But for that part, this dashed line, dash the vertical line at the n not location, this part you can see it doesn't matter. All right? Yeah? So when n less than n naught, this part, the curve, which one higher, which one lower, it doesn't matter. It could be like this, right? Yeah. 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 You do not require c multiple of g function always above f function in this belt part. Yeah, you don't require that. Yeah, doesn't matter. Not important. Yeah. Okay? So that's the meaning of this definition. Yeah. So you can see we spend a lot of time to understand our first definition of asymptotic notation, big O. Yeah, because for the remaining two, yeah, we use the similar understanding, so we do not need to spend much time. Yeah. Yeah. After we understand, so all these places, okay, yeah, all these places. So then we can quickly understand the remaining two asymptotic notations. All right. Second one, big omega notation. Yeah. This is our fifth asymptotic notation. Okay, 1, 2, 3, 4, 5. Number 5, asymptotic, big omega. Yeah, we learned the little omega before. This time, we need to use the big omega notation. Still a set, so everything the same as our previous definition, but the only place that is different is this inequality. Yeah. Here we use C multiple of G function as the lower bound of F function. Lower bound. So we change from upper bound to lower bound. Yeah. Upper bound for big O notation. Lower bound for big omega notation. Yeah, that's simple. Remaining, everywhere the same. Yeah? So here, so for the graph, you can see this time C multiple of G function, the curve must be lower than the curve of F function. Lower bound. Yeah. And also this dashed line and this part doesn't matter. For n less than n0, that part, not important. Which one larger, which one smaller, yeah, doesn't matter. Yeah. So this is our second definition of asymptotic notation. Okay, one upper bound, one lower bound. Yeah. Yeah. Then our last one. Yeah. Last one, big theta. We saw it before, but this time we write this complete definition for the big theta notation. Yeah. Big theta, we saw it before. This time we use formal definition to describe this big theta notation. Yeah. This time we need to use two constants, C1, C2. Yeah, two positive. So here you can see we need both upper bounds and lower bound. Both upper bound, lower bound. Okay? C2 multiple of G function as the lower bound of F function, and C1 multiple of G function as the upper bound of F function. Okay? Still, you need to use that N0 constant. Yeah. Still, you have that vertical dashed line. Yeah. Before this line, the shape of the curve, not important. Yeah, which one higher, which one lower, not important. Yeah. But after this dashed line, then it's important. Okay? Yeah. So the upper bound part higher than the curve of F function. Another one lower than the. Yeah? So in this way, we say F function belongs to big theta of G function, and they have same order of growth. Yeah. So for this case, yeah, in our conclusion, so our conclusion, yeah, two parts. The first one, F of M belongs to big theta of G of M. The first one. Second one, F function and G function have the same order of growth. Now let's understand this conclusion. the sentence. Yeah. All right. Yeah. Why? Yeah. Here. Yeah. Okay. Yeah. For f function, C1 multiple of g function upper bound, C2 multiple of g function lower bound. Why you can treat these two functions with the same order of growth? Yeah, we want to understand. Yeah. Yeah. Why it is reasonable to think these two functions have the same order of growth. Yeah. Because, for example, yeah, this C1 could be a very large number, right? Yeah. Yeah. We can choose C1. C1 could be 1 million, for example. 1 million. 1 billion even. All right? Yeah. Could be very large. And C2 could be a very small constant, right? Yeah. Yeah. 1 millionth. Yeah. 1 millionth. 1 billionth. Yeah. All right? Yeah. So in that case, how do you treat these two functions, g function, f function? Same order of growth. Yeah. All right. Let's understand this statement. Yeah. Yeah. All right. Yes. Yeah. Yes, we can. All right. Yeah. Remember, our goal, the reason we introduce those asymptotic notations, the reason we want to characterize our algorithms, right? Yeah. We want to define categories of our algorithms. The category, right? So the category we use g function to define category. Okay? Yeah. So g function, for example, let's say, so when the g function equals n squared, okay? Right. Now, we want to define a category of function. So we know a category could be very large, right? Yeah. The category could be very large. All right. Yeah. Yeah. So how do we define a category that contains g function? Yeah. We use the simple way. Any c multiple of g function, yeah, all the functions with constant multiple of g function, we put it in the same category. Yeah. And a c positive constant. Okay? Yeah? That is one category. Okay? Yeah. Another category, for example, Cn. Okay? Yeah. All constant multiple of n function. We put in another category. Okay? Yeah. And you can see these two categories does not overlap, right? There is no overlap. Okay? Yeah. Yeah. That's the way we define category. All right. With this definition, with this understanding of the category, you can see upper bound C1 multiple of g function and the lower bound C2 multiple of g function. No matter how large is the C1 or how small is the C2, these two functions belong to the same category, right? Yeah? Because it's a constant of g function. So the upper bound and lower bound belong to the same category. Okay? Yeah. And in this same category, f is between the two functions in the same category. Can we say f function is also in the same category? Yeah. Right? Yeah. Yeah, because it's upper bound function, lower bound, both in the same category. F is between those two functions. Then we use the upper bound, lower bound as the reference, right? Yeah, reference for F. Okay? Then we can say F function falls in the same category of G function. How about that? Yeah. In calculus, there is a similar theorem called sandwich theorem. Sandwich theorem, right? Yeah? Yeah. So this F, these three, sandwich. Yeah. One upper bound, one lower bound. Yeah. Yeah. Sandwich theorem. Yeah. Here, similar idea. Yeah. Although we do not call it this one's sandwich. Yeah. Yeah. In calculus, when we calculate the limit, okay, limit of a function. So lower bound the limit, upper bound the limit. If those two limits are the same, then the function in the middle must take the same limit. That's the sandwich theorem, okay? In calculus. Here we use a similar idea. Yeah. The upper bound function and the lower bound function belong to the same category of G function, then F function must also belong to the same category. Yeah. That understanding. Okay? Yeah. So now you feel it's natural. Yeah. Yeah. It's very natural. All right. So after this discussion, that's the foundation of our asymptotic notation. Yeah. From now on, when we talk about efficiency of our algorithms, we will use these asymptotic notations. From now on. Okay? All right. So we don't need to explain the meaning. Yeah. So after this class, we just use directly asymptotic notations. Yeah. All right. Yeah. Next, C-point 3, examples of asymptotic notations. Yeah. Let me do some calculations. Yeah. Yeah. And give you a few useful examples. All right. The first example. Simple one. Show that f function n plus 2 belongs to big theta of n. Yeah. That's a very simple one. Yeah. Yeah. And for this simple example, there are two ways we can solve the problem. The first way, because this big theta, here, for big theta, we can use two ways. The first way is the limit way. The limit way, we can use it for big theta notation. Another one is the upper bound, lower bound. So, yeah. Let's look at the limit way first. Yeah. If the limit way, let's calculate the limit. N goes to infinity. The ratio of two functions, n plus 2 over n, this limit is very easy to calculate, right? Yeah. First, we simplify it. N over n, we split the numerator. So 1 plus n over 2 over n, right? Yeah. 1 is the constant, fixed. So when n goes to infinity, 1 has no change, but the second term, when n goes to infinity, its limit is 0. Yeah. So the answer is 1. Is this 1 positive constant? C, right? So if the limit of the ratio of two growth functions is a positive constant C, then we have this big theta notation. So that is the first method. Yeah. The second method, we need to apply the inequality, upper bound and the lower bound. Yeah. our f function. Yeah. Now we need to find the upper bound, lower bound, C1, C2. Yeah. All right. First, let's look at lower bound. Yeah. N2 greater than N. Easy to see that, right? Yeah. Yeah. So this N, it's a constant multiple of N, right? Constant multiple. 1 times N. Yeah. So we find the lower bound. Yeah, but this inequality holds when N greater or equal to 0. Yeah. 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 Although for N negative, this inequality also holds, but we never consider negative N, right? Our problem sizes must be non-negative. So that's why, yeah, we do not include the negative N values. Yeah. Then, C2 constant is 1 from this inequality. Next step, can we find C1 constant such that N plus 2 less than C1 constant of N? Yeah. Here, there is a plus 2 thing. Okay? Yeah. How do we handle this plus 2 constant here? Yeah. And we want to get upper bound. C1 constant multiple of N, that is the upper bound here. How about we replace 2 by N? Is it a generous way to make the function value larger? Yeah. Upper bound, we go larger direction, right? Yeah. We go larger direction. Yeah. Yeah. So in general, most of the time, N greater or equal to 2, right? Most of the time. Yeah. But we put a condition here. When N greater or equal to 2, if we replace 2 by N, we go larger, right? Yeah. We go larger, then we get upper bound 2N. 2 times N. With this condition, okay? With that condition, this one, in our definition, that's the N naught. That's special, positive, non-negative integer number, right? That's the N0 constant, yeah? But here, you need to have both inequalities, right? Both must be true. If both must be true, then you'll pick this one, right? Yeah. Okay. All right. So C1 equals 2, C2 equals 1, and N0 is this 2. So that's the definition way to see f function belongs to big theta of g function. Yeah. So you can see we need to do more work than the first method, right? First method much easier, yeah. But yeah, here we want to practice the definition way. Yeah. All right. That's our first simple method. Yeah. All right. Then the second example, yeah, show n cubed belongs to big omega. Big omega with a lower bound, right? The constant multiple times the g function n squared. Yeah? Yeah. But we can see n cubed greater or equal to n squared for n non-negative integers. Yeah? Well, always true. Always true. So the C constant is 1. C constant is 1. N0 is 0. Yeah. So we get a, by the definition, yeah, yeah. So we can prove this. Yeah. Very simple example. Yeah. All right. Yeah. Next one, our third example. Yeah. All right. Show that n plus 2 parentheses cube belongs to big theta of n cubed. big theta of n cubed. So for this example, we have two methods. Yeah. The first one, the limit method. The second one, upper bound, lower bound. Yeah. So let me do the first method quickly. Yeah. Find the limit. N plus 2 cube over n cube. We want to calculate this limit. All right. Then we apply the property of the limits. Yeah. All right. All right. First, yeah, because this cube thing, we can put a cube outside this fraction. N plus 2 over n. We do fraction first. Then we do cube. Yeah. All right. So let us simplify. One plus 2 over n cube. Okay. Yeah. But when we take limit, we can do it inside the parentheses, right? Yeah. So the limit property. So we're allowed to take the limit inside the parentheses. Yeah. So that is 1 plus 0 cube, right? 1 plus 0, it's 1. 1 cube, still 1. 1. It's a not positive constant. The ratio of the limit, positive constant, that tells us this big theta relationship. Yeah. So that's the limit way. Yeah. The next one, definition way. All right. Definition way, upper bound, lower bound. So this time, we need to find upper bound, lower bound, constant multiple of n cubed. Yeah. C1 constant, C2 constant, such that C1 multiple of n cubed is greater or equal to f function, and the C2 constant multiple of n cubed is less than or equal to f function. How to find C1, C2? Yeah. With the cube, how to find C1, C2? Yeah. All right. Can you see, even with cube, yeah, because the parenthesis part greater than n, right? Then we raise to cube, both sides. Because they are non-negative numbers, when you raise to cube, still. If it's a negative number, then you may have problem, right? If a negative number, when you have problem, so when you raise, yeah. Sometimes, right? Sometimes you have problem. Sometimes you're fine. For negative one. Yeah. But here, non-negative, so it's always correct. Yeah. All right. Yeah. So here, n greater or equal to 0, you have this lower bound function, and C2 equals 1. Yeah. Now, next, let's look at the upper bound part. Yeah. We need to find the C1, constant multiple of n cubed. Okay. To get upper bound, yeah, so we replace n plus 2 by n plus n, and we want to go larger direction. Yeah. Yeah. So we get a 2n, but we need a condition, right? We need an n greater or equal to condition. That's our n0 number. Yeah. All right. Then we raise to the cube of 2n. Cube of 2n. That's 8 times n cubed. Yeah. So this 8 is C1 constant. Okay? Yeah. So you find both C1, C2 constant and your N0, 2. So that's the definition. Okay, all right. Yeah. Yeah. So in this example, you can see, yeah, pretty straightforward. Yeah. All right. Yeah. But when we calculate, when we all right, so m plus, yeah, all right, so y, yeah, so you are okay with this step, right? Right? Yeah. And by the, yes, to, yeah, you know the property? Yeah.
That's the way I wrote it.
Yeah, yes. Yeah. All right, this property. Yeah. All right. Yeah. Another comment, yeah, because I assigned a similar question to students before. I remember I did this m plus 2 raised to the 5th. So I asked students to show belong to big theta of n to the 5th. Okay? Yeah. You can use the similar method, right? Yeah. Yeah. But many students, when they work on this problem, they expand this polynomial. You won't do that, right? Yeah. But so many students did that. Then got very messy. Complicated formula, then find C1, C2. You know, too much work. Yeah. So do not do expansion. Yeah. Using this way, all right? Yeah. Yeah. So you get inequality without exponent number, then raised to the power of that number. Yeah. They're much easier. Yeah, yeah. Just something. Yeah. But recently, I do not assign proof questions like this. Yeah. All right. Yeah. Next. Yeah. So let's try to do another example. Yeah. So for this example, show. Yeah. Log function belongs to little o of n. What's that? Little o function. Little o, we know limited. Yeah. Ratio of these two functions, the limit equals 0. That's the little o. Yeah. All right. Let's calculate the limit here. But when we calculate limit, so there is some, actually we did similar things before, right? Yeah. So n is a discrete variable. Discrete variable. All right? Yeah. Because discrete variable, if you want to take derivative, you cannot do it directly. Yeah. So for that reason, we switch to the continuous variable version. X is a continuous variable. So log function of x over x, it's a continuous version. Continuous version, the derivative exists. So we can apply the L'Hopital's rule, right? Yeah. Because this is a infinity over infinity indeterminate form. Yeah. So we can apply L'Hopital's rule. Yeah. L'Hopital's rule, we need to take derivatives. Yeah. So for the continuous variable, the function of continuous variable, we can take derivative. All right. Yeah. Yeah. But here we need to use base A greater than 1. All right. Yeah, so taking derivative, apply the formula, so we have this one after simplification. Yeah. Natural log of A is a positive constant. It's positive. Okay? Yeah. All right. Yeah. So then when x goes to infinity, it's 0. Yeah. All right. Yeah. Because denominator will be infinity. So 1 over infinity. So the limit is 0. Yeah. All right. Then we go back from continuous variable to discrete variable. We need to go back. Oh, yeah. So here, yeah, let me just write a few more steps to go back. Yeah, because we need to, after we get the result for the continuous variable, then we can go back to the discrete variable equals 0. Yeah. Yeah. Because remember, this step, we apply the definition of limit. Yeah. I explained before. Because when x approaches infinity, which way? In which way? Any way works. Here we use this 1, 2, 3. Okay? Yeah. And this way to infinity. Then that's the discrete values. Yeah. All right. So after that, then our conclusion is, based on the definition of little o notation, log of n belongs to little o of n. Yeah. Yeah. So that's the way we show. Yeah. All right. So this result, okay, yeah, although it's a simple result, this result, yeah, simple, yeah, but it is useful. Yeah. It is useful. All right. Yeah. So let me go to another example. So we have some time. Yeah. Yeah. Let's do another example. 2.5. Yeah. This time, power function n to the d power function belongs to little o of exponential function a to the n, but the a here must be greater than 1, and the d here must be greater or equal to 1. Yeah. So actually, later we will see if d is positive, it's okay. It is correct for any d positive, this condition. Yeah. So we can, improve it to that condition. Right. But here, in this example, why I assume d greater or equal to 1? Because for simplicity, okay? Yeah. So I want to make it relatively simpler. Yeah. All right. Yeah. So let's work on this version. Yeah. But later we will extend it to that version. Yeah. Extend it. Yeah. All right. Yeah. So to solve this problem, we need to take limit. Yeah. Little o, we need to take limit. Yeah. But when we take the limit, we plan to apply L'Hopital's rule, right? Yeah. We plan to apply L'Hopital's rule. When we apply L'Hopital's rule, we need to take derivative. We need to take derivative. Yeah. All right? Yeah. So, yeah. But we know the derivative of exponential function, also the power function. Yeah. All right. We know both formulas. Yeah. All right. So then, to do it, yeah. Yeah. Because here you can see this problem relatively hard, comparing with the previous 4 examples. This one, yeah, much harder. Yeah. So when we have question relatively hard, yeah, remember we learned one strategy before, one problem solving strategy before. Here, I'd like you to recall a little bit. Yeah. When we solve a problem relatively hard, what is some special strategy that we can apply in this situation? Consider multiple cases. Yeah. Yeah. So here, for this D, can we consider multiple cases for D? Think about the D. Because here, this D not necessarily integer, right? Nobody says D is an integer. D could be non-integer. If D is non-integer, relatively hard, right? Yeah. Yeah. Relatively hard, non-integer. Yeah. All right. So then, based on by our strategy, can we make assumption to let D be integer? How about that? Because our strategy, we consider simple case first, right? We consider the simplest case first. Yeah, so that's strategy, okay? So here, what's the simplest case? Make a D integer. D positive integer, yeah, because D greater or equal to 1. So our first case is we assume D is a positive integer. If D is a positive integer, then when we take derivative, then it's very simple. Yeah. That's the reason. So we want to make D positive integer. All right, now let's prove it for D positive integer. All right, yeah. Let's do the work. Okay, do the work because we need to apply L'Hopital's rule. So we need to switch to continuous version. All right, then take the limit, the power rule, numerator, denominator. We have the formula. Right? Yeah. Then after simplification, yeah, simplification, and we can take another round L'Hopital's rule, right? Yeah? Yeah. Because if D is a relatively large number, we have infinity over infinity indeterminate form, right? Yeah? Because whenever we have infinity over infinity indeterminate form, we can always apply L'Hopital's rule. Yeah. All right. So this is the second time apply L'Hopital's rule. If D is greater than 2, we can do another round L'Hopital's rule. Yeah. Keep doing. Okay? Yeah. Keep applying L'Hopital's rule until the exponent of the power function x is 0. D minus D. Yeah? It becomes 0 then. We cannot apply L'Hopital's rule anymore. Because it's not indeterminate form. All right? So we have to stop. After simplification, we have the limit of numerator d factorial. D factorial. Denominator natural log of a to the d, then times exponential function a to the x. And when x goes to infinity, because a is greater than 1, okay? Yeah. X goes to infinity, so this limit must be 0. Yeah. That means the whole limit must be 0. Yeah. Right? Yeah. Whole limit must be 0. Yeah. So we prove the case when d is an integer. The simplest case, we prove it. Okay? Yeah. Yeah. So that's the simplest case. By our strategy, we always start with the simplest case. Yeah. That strategy. But if next round, if we need to remove the assumption, right? Yeah. So this assumption, that's the first step. Our next step, we need to remove this integer assumption step. Yeah. Yeah. After we remove, how to prove it? Yeah. So I leave it to next class. Yeah. So next class, first we complete this example, then we have two more examples. Two more examples. Those two more examples closely relate to our homework questions. Yeah. Regarding homework question, this weekend I will post our homework assignment number 1 questions. Yeah. So check the Canvas. Yeah. So usually I give you, more than 1 week, less than 2 weeks. Yeah. Yeah. So let me see. If I have enough time, I will give you 2 weeks. Yeah. Because I need to check before the midterm, how much time do we have? Yeah. If we have more than 2 weeks, then I will give you 2